Okay, today we're going to talk about graphs. Hopefully y'all seen a evolution of our data structures. So I'm going to see if y'all can guess what comes next.
Graphs.
Right. So at first we had a binary tree where we had a guy, a root, go to maybe two different children, and then maybe they have some more children.
Is a graph the one that has like a million children and it goes in a circle?
Hold on.
Like
All right.
evolution trees?
So that's a binary tree. And then with a B tree, we said you can have more than two children, so maybe we'll have another guy here. And maybe this guy will have lots of children over here. And maybe this guy will have some more children. And he could have tons of children in between right here, maybe a bajillion. Sure. So what would be the next step here? Right. And that would be?
Lots and lots and lots of children.
Well, with the B tree, you can have any number of children. So I don't think that will.
More organized children.
More organized children? No, that's pretty organized.
I don't know.
If I were to totally, blow your mind, I would draw an arrow from here to where?
All the way back up to the top.
It goes both
Oh! Okay, what just happened?
ways. It goes both ways.
It goes both ways. In fact, we might have
That's disgusting.
another one over here, and maybe he'd go to over here, and maybe this guy would go to over here, and maybe this guy would, just for the fun of it, come back over here.
That's
disgusting.
nonsense. I don't like it.
Why not?
I guess.
That's gross.
So this is graphs,
That's gross.
which actually is very, very useful. And used all the time. I mean, Google Maps is just one giant graph. Let's see. So objectives, we're going to learn some stuff. I really think that's what it should just say. Wow. Okay. Introduction. I don't know how to pronounce this guy's name.
Kongsberg?
That was pretty good.
Kongsberg?
Koininsberg or something. So the river Prigel flows around the island of Koinephof and then divides into two branches. So you have this island. You have a bridge here, 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 a bridge up here, and a bridge down there.
That's too many bridges.
You can never have too many bridges. So starting on one land, can you cross all bridges exactly once and return to the start? Any land. From this island, maybe that island, maybe up here or down here. Can you run through this and cross all bridges exactly once?
No.
Why?
Because you'd end up like back at one of the islands and you'd have to go back out. So you'd have to cross at least one of them twice. Correct?
Yes. Have you done this program before?
No, I was just, in my head I was just looking
Yeah.
at all the bridges.
Okay, maybe this is your calling in life.
Looking at bridges?
No, graph theory.
Looking at bridges?
Looking at bridges? All right, so in 1736, Euler represented the problem as a graph and answered the question no. All right. Do you see how this graph on the right is the same thing as this picture over here? No. Maybe? Yes?
Go back. Yes.
Island, top land, bottom land, other island, the bridges.
I gotcha.
Over the past 200 years, graph theory has been applied to various problems. Circuitry, thermodynamics, highway maps, analysis of okay, sure. Analysis of circuits? Okay, really? Modeling, blah, blah, blah. It's been used a lot, all over the place.
Just say it's been used a lot.
It has been used a lot.
I think you should just like.
All right, so,
put stuff-
all right, fine. We'll just get to the math then.
Just put like stuff over these sides and be like a lot.
All right, well, here's your definitions. You ready for your definitions?
Mm-hmm.
So what's that first thing mean?
So seconds.
No.
Oh, the first
Anyone in discrete math?
No.
Sydney?
You're discrete math.
Okay.
Read form.
So A is an X, which means A is an element of set X. So Y is a subset of X. Basically, where if A is an X, everything that's in Y is an X too. But that doesn't mean everything in X is in Y.
Right.
So basically, if Y has 1 and 2, and X could have 1, 2, and 3, and Y is still a subset of X.
Wow, Jonah.
The intersection, basically what it's saying is that it has to be of both A and B to be in the intersection. Basically, if you think about it, it's where they cross, where they're the exact same.
So when you intersect, you actually create a new set.
Right,
And then that new
so
set has to be in
if
both A and B.
A is 1, 2, 3, B is 1, 3, 4, 5. Then the intersection is 1, 3. Union is just both sets A and B together.
You good, Jonah?
Sure.
Yeah.
I think I
All right,
understand.
we're going to keep
A
throwing
is
some
1,
terms.
2, B is 3, 4.
So, what's that one?
Oh man. That one's a little more complicated. You take an element from A and put it as the first part of the ordered pair, and then you take an element from B and make it the second part of the ordered pair.
You combine the two elements.
So it's a set of all ordered pairs of elements of A and B. Basically,
Yeah.
you start with A and you go through all the ordered pairs of AB, where A and B are inside of big A and B.
V is a finite, non-empty set.
You good, Jonah? Or you want an example?
Huh?
Good.
I think I'm good.
All right. So then a graph is basically a collection of vertices and edges, where V is a finite, non-empty set of vertices in G. So those are going to be numbers. And edges are a subset of all the possible ordered pairs of V and V. So all the possible vertices. Elements in E are pairs of elements of V. E is called the set of edges. So the edge is what's going to connect your vertices, or sometimes I will call them nodes. Back to our picture. These circles are your vertices. I will sometimes call them nodes. And these arrows are your edges. Any questions? Awesome. So a directed graph, or a die graph, elements
Die.
elements are ordered pairs, and undirected graph elements are not ordered pairs. So the picture I drew on the board, is that directed or non-directed, or undirected?
Non-directed.
Now the arrows, they have arrows showing you which way they go.
Oh, it's directed.
So they're directed. Yeah,
Oh, Prim's algorithm.
good old Prim.
Lesson has the.
Oh wait, were you in my...
No, I shadowed the class.
Oh, that's why. Okay. So let's see. If UV is an edge in a directed graph, origin U, destination V. So, in other words, if we were up here and we gave these numbers, like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 100, 300, and 404, what would be an edge?
An edge would be wherever the arrow is itself.
So give me an edge.
The 300 pointing to the 104.
So 300, comma 404.
104 or 404. Whatever the number is.
That's 404.
Oh, you can see it. Yeah.
404.
That's an edge.
So another one would be from 0 to 300. Notice that you have to start with the origin and then you have the destination.
Can there be more than one?
So would another one be 100 and 0?
Let's see. 100 to 0. Yep.
Okay. Did I get it?
It
But
can also be
100
0.
and 404 does not exist.
Yeah.
That's not an edge.
It can also be 0 to 100 because it's 0 going to 7 then going to 100.
Nope.
No.
No. That's a path.
Oh, a path.
That's a path because you have multiple edges. An edge is one link.
Okay, I see.
Now, to answer your question, can you have multiple edges? It is actually possible to have another one right here. But we'll get to that in a moment, okay?
One step at a time.
You keep using that word, Caitlin. I don't think it means what you think it means.
What?
You?
I didn't say you.
Oh, who said that? Sydney?
In a moment.
No, I didn't say it was them.
Okay. So subgraph H of G is if all the vertices of H are in the graph and all the edges are in that subgraph. Okay, this is actually pretty easy. You just draw a circle. Whee! There's
Draw
no
a
subgraph.
circle.
Nice.
So you just have these edges and those three vertices. All right, good. Also, that's a good question. Is a tree a graph?
Why not?
Is a binary tree a graph?
Yes,
Yes.
because you have pointers.
Is a B tree a graph?
Yes.
Yeah.
So basically, it's all
But a graph is not a B tree.
Not necessarily a B tree.
built on a linked list.
What?
All the past, with the exception of heap, you would have graphs and trees are built upon linked lists, aren't they?
Graphs?
No?
No, not necessarily.
Never mind.
Okay. Oh, here's some more graphs.
Yay.
What do you think that bottom graph is trying to represent?
A map. Cities and destinations with airports.
That's a good one. Yeah.
Or
Yeah.
various destinations. That's possible.
whispering?
There's a Caboose-isms poster and it says, "My name is Michael J. Caboose and I hate babies."
I need that shirt. Or that shirt.
Wow. Wow. People are just not going to pass this course.
Hey, we're gonna pass.
All right. So here's some more graphs. Notice that in this one, it's kind of like a tree where it all flows to the right. Though not exactly a tree because you have 4 going back up to 2. In this one, you have some cycles because you can go 0, 3, 6, back up to 0. In fact, I think you can always cycle out. Oh, except for if you're at 7. 7's the dead end.
7's the dead end.
And this one. So adjacent. 2 vertices are adjacent if there's an edge from one vertex to the other. All right. What are some vertices or nodes that are adjacent here?
That are adjacent.
Yes. Let me
Why did you shoot?
I shake this table.
Oh.
Then I get off of it, it shakes you up.
What was the question again?
Name some vertices that are adjacent. So 0 and 1, there's an edge between them.
So anything that has edges between them?
Yes. 0 and 1,
Everything?
0 and 300. What?
So like everything?
0 and 7 do not have an edge between them.
Okay, anything that has an arrow in between them.
An edge.
Yes.
One edge. Not a path, an edge.
0, 7.
So 0, 7, 2 and, oh, that's a 3.
There's 0 and 2.
Make sure it's a 3.
Yeah, that was not obvious.
So 3 and 100.
Mm-hmm. So what are things that are not adjacent? By things, I mean vertices or nodes. 0 and what?
2.
No, there's an edge right there.
Oh.
3 and 300.
3 and 300, right. There's no edge going from 3 to 300. All right. Any other questions? All right. Let's see, an incident. If edge UV, there's an incident on U and V. What? Okay. Anyways, parallel edges associated with the same pair of vertices. So that's what I was talking about earlier. You have an edge here, you can technically have another edge right here. So these are parallel. That'd be like if you have more than one flight going at the same time. Simple graph has no loops or parallel edges. So what would we have to remove to make this graph simple? Well, we have to get rid of this thing. Get my eraser. What else would we have to do? Well, there's a loop between 1, 300, 400, 404 back to 1. So we'd have to get rid of one of these edges. Let's get rid of this edge. And this 100 could go back up, so let's get rid of that edge. I think now we're simple. Yeah, we're simple now. See what we did there?
Mm-hmm.
So a path is a sequence of vertices such that there are edges between them. So that's like what we were talking about earlier. A path from 0 to 4 could go 0, 1, 4. Or it could actually be 0, 300, 400, 1, 4. Which path is better? Ooh, there's a good question.
Whichever one takes less time.
You would get more information going the long way. But the short way would get you to your destination faster.
Maybe. I mean, if this was travel, what if that trip from 0 to 1 took 3 days? And then all the other paths took 1 hour?
I don't go an hour one.
The multiple 1 hour ones would be better. All right, connected vertices, there's a path from U to V. So that's, if there is a path, they're connected. So a simple path in which all vertices except possibly first and last are distinct. Cycle is simple path and where the first and last vertices are the same. So we don't have a cycled yet. But we could create one by putting this back in here. And you go 1, 300, 404, and back to 1. Now you have a cycle. All right, connected, the path exists. Oh, a connected graph, path exists from any vertex to any other vertex. And let's see. And then strongly connected, any two vertices are connected. Basically, there's a path from every vertex, or not path. There's an edge, connected path exists are connected. Any two vertices in G. A path exists from any vertex to any other vertex. Strongly connected, any two vertices in G are connected. Wait, what's the difference between connected and strongly connected? Vertex, right? Any two vertices in G are connected. All right, so what do we want to do? We want to write programs that process and manipulate graphs, so we need to store them in memory. We have two basic ways to do it, adjacency matrices and adjacency lists. Right?
Yes. Sure.
Right.
Wrong.
Oh my goodness, these slides are terrible. What? Wait, what? Wait, really? That's all we're going to do? Wow. That's terrible.
That's it.
That's it?
How rude. That's it.
All right, so I'm going to stop here.
That's all she
That's
wrote.
it.
Yeah.
That's all, folks.
Ta-da!
And I'm going to let y'all have plenty of time to work on your labs and your project.
That works.
Yeah.
Ethics paper, because I did assign that today. All right, lights.
Camera. Action.
Any questions
No way,
before I
you
get?
went to
Oh, okay.
downtown yesterday. How was it?